Hello everyone, and welcome to another video on aspen. Now in this video I'm going to go through the things we covered in the lecture on Thursday. This is going to cover the electrolytes, and we're using electrolyte systems as, again, just a reminder, as a way of introducing how to do multi-component, multi-step processes with multiple units, and how aspen deals with reactions and in its flow system and how it handles that, and also give you an example of how you can adjust parameters and adjust things to suit what you want and make things work easier for you. So let's start by first going to, and again this opens up weird, so I'm going to pull it to the side so you can see the file open, file new, and we're going to go to the electrolytes, and I'm going to run electrolyte minimetric unit, and here we're going to do a combination system where aspen is going to run first a mixer. We're going to be putting mixing an acid solution and a base solution, NaOH and HCl, and first mix it and then send it to a flash unit. So let's get this started. So the first thing we need to do is, and you'll notice one of the interesting things about selecting a electrolyte system is we don't get any red things here, and that's because it's already has the methods selected. Here it's doing the electrolytic NRTL method, which you can see electrolyte NRTL gives you a highlight of what it is. It also already has one of the components listed, H2O, which is all it cares about at this point. But we're going to add in HCl and NaOH, and as we mentioned in class, these aren't the only things that do exist in this solution, right? We have when either of these two entities enter water, you're going to actually have NaOH break into the ions of sodium and hydroxide. You're going to have HCl break into the protons and HCl. And the protons will exist in the hydronium ion format. Now, what's interesting here is we also could potentially have a combination of NaCl, or the salt formation. And we would like to have all these components represented in aspen. So we can use the electrolyte wizard as a quick help on how to do this. And this is just going to set us through these steps and what we can follow. So I'm just going to select all the defaults and go from there. It's asking me what components I want when I say next. And so here it's saying available components are the sodium hydroxide and HCl. We want all of these to be considered in considering what is we want. The type of ion we want. Do we want hydrogen represented as a H+, or do we want a hydronium ion? I'm just going to stick with the default here. Do we want to include salt formation? And the answer is yes, definitely. Ice formation, no, we're not going to be in a low enough temperature, so we don't need to include these things. So here you go. Now that we've clicked next, and I'll go back, I'm just clicking next to go through each one of these steps. So now that we click next, you can see the aqueous species are all listed here of what it is that are considered aqueous, and then you can see all the salt species that is being calculated for. Now in these salt species, NaCl can form, I can see that. NaOH, water hydrate form, or the solid form, I'm going to assume that both of these won't exist, mainly because these are going to be hydrophilic systems. I can't imagine in this system that we're having that that the sodium hydroxide will precipitate out, so I'm going to ignore those reactions. So in this case here, we're just going to assume fully disassociating ions. So NaOH going to sodium hydroxide, yeah, that's all we care about. But I'm going to remove the components that I think aren't relevant. So it's these two salt forms. So we only care about NaCl in this. We don't want to change the electrolyte system. We don't care about and we'll stick with that property method, and we'll click next. And now, as we mentioned in class, we have a couple of different options here. We can say, do we want to run this in the true component approach, in all the ions and all the species being separately dealt with on a one-to-one basis, or we can do it in an apparent approach where everything is just lumped up into what we created as HCl, NaOH, and water. True component's more interesting, and we can always go back to apparent conditions. A parent is going to have less information than the true, and we can always gain back less information later. So we'll just stick with true component for now. And this will cause parameters change. Yes, of course, that's what we want. Yes, of course. And that's it. And so we can say finished. Here, if you want, you can actually, if you want to look at this information, we can review Henry's components. So we can click that and we can see select Henry's components, available components for review. We can select all of them and say available components, selected components, close. And so we can actually review all of those. Review chemistry. We can see what the chemistry is in our system here. And you can look at all over here, all the reactions are happening. We have equilibrium reactions and these dissociation reactions. We can look at the equilibrium constants and how they're calculated in these assessed settings. So the equilibrium constant, you have the equation that's being used to define the KQ as a function of temperature, and all of the coefficients that are being given here. And obviously HCl and H2O is being assumed to be a full dissociating system, so there shouldn't be any equilibrium constants, and so it's not. And so we can see that. And other than that, we can say close, we can say finish, and now we have all of our systems set up. We can go to our methods, we can go to our parameters, go to our binary interaction parameters, Henry's coefficients, and you'll notice here in the methods, it's asking us just to look at them. They don't care other than the fact that we're just looking at it. And once we looked at it, then we can say, okay, this is just to confirm that these numbers are in agreement with what you'd anticipate for these systems. If at some point you have a reason to change these, you can at this time. And so these are all selected, and we are good to go. And that's it. So now we can go to our simulation. Oh, I forgot to mention, go back to properties. One other thing we can look at here is we showed you the chemistry from that help window, but you can also go to the chemistry by looking and clicking in the chemistry tab under properties. If you go there, you can look at your global chemistries, and this just gives you another source of that information that was created previously. And so in this case here, you can look at, say, this sodium chloride salt dissociation, and in this dissociation you're just seeing the stoichiometry of the system. So we're having 1 sodium and 1 chloride generated for every 1 mole of NaCl being disassociated. And that's all that's setting up, is the stoichiometry. And then here you can specify the equilibrium constants again. So if you missed it in the electrolyte wizard, you can still get to it because it's still fully available. So now let's go to the simulation. And in the simulation, we can say here we're going to have a mixer. I'm going to place a mixer in there, and then we're going to have a separator, and the separator is just going to be a flash. And so we're just going to pump in 2 streams of a HCl and NaOH stream going into a flash unit that's going to be separated into a vapor phase and a liquid phase. And so in this case here, we're going to create 2 streams, and I'm going to click and drag and move this up so it's easier to see. That's the 1 stream in. We can click and drag and move this out. Oops. There we go. That's the 2nd stream. And then we can click and drag, connect those. Connect. And remember, we're always clicking the reds for those connections. These little blue ones here are not of interest to us. These are the decant streams. So we can click that. Now I'm going to rename these streams as HCl, NaOH. Oops. Let's go back. I don't want to edit that stream. Let's go back to our main flow sheet. Let's double click this, and we can say mixed, because that's going to be what's coming out of the mixer. We can call this vapor. And we can call this one liquid. So that will be the bottom of the flash unit. And so finally, we have all of the flow sheet set up. It's blue. Now note, if it's not blue, that means some of these streams are not connected properly. So make sure that all the inputs are satisfied in the units and so forth. So make sure that that's connected correctly. Now that we have that, we can go to our streams. Any stream that doesn't have a origin point, like all these free-floating input streams, is going to need conditions set for it, specified. So in the terms of this problem, we're going to say this is 25 degrees C and 1 bar. And now you'll notice here it's giving us all in terms of mass flow. And we have everything in terms of mole flow. Every time I click on the next stream and everything else, it's always going to say mass flow. And that's going to get tedious. I can change it each time, but that's a little tedious. So I can go back to setup. You can see setup here in this option, and this gives us global parameters and what the input mode is that we're going to be setting. Obviously, you can change from steady state to other conditions. We'll stick with steady state. The one I want to change, though, is the flow basis. I want to move that to a mole flow instead of a mass flow. Now we go back to here, HCl, since we already opened it, it's still mass, so I'll have to change this one. But all the other streams from here on out will be opening up as mole flow. And so I'm going to input these as the total flow rates now. I'm going to say this is, for H2O, is 10 kilomoles per hour, and the HCl will be 1 kilomole per hour content. Now, since I'm adding total flow here, I'm going to leave this blank. Do not fill in a flow rate here and here. Down it says mole flow. I can do the same thing for NaOH. I'm going to say this is 10, and I'm going to say this is 1.1. There we go. That's all very good. And we need to enter in the stream temperature and pressure. There you go. Good. So now we are satisfied. So now we can go to blocks. And the only block, oh, I forgot to name and label our blocks. So I'm going to call this mixer. I don't like saying B1, B2 because that's not very specific. And I'm going to say over here, this is the flash, not glash. Flash. There we go. So we have flash, mixer, and we are happy. So now flash is still not described because it has two degrees of freedom. We got to specify those two entities that we want to make it fully satisfied. In this case, we can select what we want to specify. We can select the temperature and pressure as the two components. We can say a duty and a pressure, what the energy flow rates are going to be, and a pressure or a temperature, or a vapor fraction. For this problem, let's just specify vapor fraction and a pressure. The first thing we can say is the problem statement states that this is isobaric. Now the interesting thing in Aspen is we can give an absolute pressure. Anything greater than 0, it'll just treat that as the pressure of the system. However, if we say 0, it's going to treat it as a gauge pressure then at that point, because obviously, and so it's going to say whatever input it is, pressure coming in, it's going to say it's not going to change it. It's going to keep that same pressure. If I give a negative value, you're not going to actually have a negative pressure because that doesn't exist. But what it'll entail that is it'll be a pressure drop then. So it'll be whatever the initial input pressure is, deltaed by the pressure drop for this. So I'm just going to say 0 to make it isobaric. And the nice thing about this now is, and one of the conveniences is I could specify 1, because that's what the streams coming in are, and that's 1 bar, correct? And so that'll be isobaric. However, if at some point in the future I adjust this and I change the flow, the pressures of the units coming in as saying 5 bar, and I still wanted to keep it as isobaric, then I would have to come back and remember to change the pressure on the units as well. However, if I just say that this is 0, then it's going to take whatever the flow rate pressure is, flow input pressures are, and just take those as given. So let's just leave that. And in this problem, we specified a vapor fraction of 0.575, and that is it. Before we run, I think we're good, so we can actually click next just to confirm we have everything. And yep, it says we do. But before we do that, I'm going to go to our property sets or setup, and I'm going to specify some additional report options. In particular, I'm going to want to add in mole fractions coming in here. And I also want to see some properties over here. For example, I want to know the bubble points in our system. I want to know to make sure that whatever the vapor, whatever the flash drum is specified, it should have the same temperature as the bubble point of the inlet stream. So let's confirm that and add that into our data that we're going to output. And then internally, or initially, we can also get the apparent mass fraction of our system as we want. And that would be kind of useful as well. So we're going to select these two, say, oh, close. We're all happy. Now we can run with a little arrow. Let it run. And as I mentioned before, my version likes to do that. So I am going to cancel that because I do not care. I'm going to go to the streams. Let's go down to our results summary, our results status, our streams, and we have our temperature, pressure, and everything else all hunky-dory. If you scroll down, you can see here, first and foremost, some of the things that are interesting. Our inlet streams, our HCl, and our NaOH. I'm going to change the order here. Let's change so this is a little bit easier to follow. So I'm going to make this, oh come on, NaOH mixed, and then this can be liquid. That way, this is input, mixed stream, then the two outputs from the flash drum. So the first thing you can check by seeing that is you can see here, oops, oh there you go, is that the temperature 25 and 25 is entering into the mixture, and it's leaving at 62.9 degrees C as the temperature, meaning that this is an exothermic mixing, and all that heat that was generated went into raising the temperature of that outlet stream. The next thing you can check is seeing, well, what's coming in, you're flashing that unit, and the liquid stream bubble point should be the equal to the temperature of this flash unit. So this is 109.5, the temperature of the flash unit, and you can look down here at the bubble point temperature, and sure enough, at this salt concentration, the bubble point for water and this NaOH HCl mixture is 109.5. So this makes perfect sense. The vapor, being pretty much just pure water, is at the pure water 100 degree C temperature. And you can scroll down and you can get all the elemental information as well. You can see the H2O flow rates, NaOH, but interestingly enough, one of the things you can see here is that NaCl solid has a value of 30.4 kilograms per hour. In other words, we're precipitating salt in the flash unit, and it's coming out with that liquid stream as calculated here. And you can actually look at this and look at the sodium concentrations, and you can look at even the parent mass fractions of water, NaHCl, and NaOH as inputted in streams. And so you can actually do the mass balances using this as well to confirm all this data. So this is just a really nice way of seeing how Aspen can handle the reactions, how it can use this and apply this to understanding the way reactions, mixing, and temperatures can be are calculated and handled. Now we can actually use this and start playing games, kind of asking ourselves, well, now that we know this liquid is coming in at this at this rate, what if we were to add another unit to dissolve that solids? Can we do it? And how much flow rate could we do? And this was a question I had asked you in class to do. Right at the end, we didn't get a chance to really do this, so I went ahead and gave you an example. But one of the ways you can always do this is you can add in another mixer, and then I can take this, connect that liquid to this mixer. I can add a new stream. I can add a new material stream here of pure water. There you go. And we call this dissolve, because we're trying to dissolve the salt in there. We can add this as, just call this water. And you'll notice now that we added a new input stream. We have a new water temperature there. So we're going to say this is all, again, ambient, 1 bar. And now the question becomes, well, what can be the flow rate of this water? And let's change this to mole fraction now. I'm going to do this 1 as pure water and 1 kilomole per hour. And if I go back to my simulation, you'll see now that everything is satisfied. We have these little yellow squares, meaning there's been changes. So even though we have results, these results are no longer valid for the new changes. We have to rerun it to get the new results with a new flow sheet. And that's all that's telling us. But really what we can do now is we can start playing games by asking, okay, Aspen, hey, if we change this flow rate of water, will we dissolve the salt that's in this liquid? And we can check that by looking at the concentration or the mass of solid salt in that run stream. So if we run this, we can display this results form and say, okay. Or we can go down to, let's go to streams, and we can go down to our dissolve stream here. And if we look at salt, NaCl solid, or where is it? Mole, that's mole fraction. I want mole fraction, I want mass fraction. Mass flow rates of our salt here is from 30 kilograms per hour. And we're now at 24 kilograms per hour. So we haven't dissolved it very much at all. So we can actually increase it again by going back to our water stream, and we can up this. I'm going to up it to 5 kilomoles per hour and click run. And we can go to our streams and dissolve. We look at the solids, and sure enough, at 5 kilograms per hour, we no longer have any solids in that mixture. Now I know that was the answer. It's between 4 and 5 that we fully dissolve it. We showed in class briefly how you can actually make Aspen iterate for you to find that solution rather than you having to do it manually. But the nice thing is you can get a sense of how just quick and easy it is to ask a simple question, let it run, and get that answer back. This can become obviously much more complex, but it's a very nice way of seeing how this information can be obtained and learned as we go along. And so beyond all that, the final point here, look, actually one thing I should point out is we did get results with warnings. We can click those, see what those are. Attempt to use model without a solvent. Okay, so here it's just yelling at us for some activity coefficient errors that were for the solvent systems in this case, but that's a fine result for now. That's not a big deal. But anyways, one of the things to be careful of is if you do see these warnings, to read what they are and come up with a check to see if they make sense or if they're valid or not. Systems, there are really 3 modes to which Aspen can output data. One without warnings, one normal with warnings, or just crash entirely. Crash entirely won't, or errors just won't converge and give you rational results. The warnings, they can be rational depending on what's happening. In this case, this is completely fine, but sometimes the warnings may actually give you errored values as well. So once again, Aspen isn't going to replace your ability to having to think about what the results are and if it makes sense, but it does give you a good basis to start from and learn more from the system. So with that, we're going to leave it there. That is, in general, how you can actually add multiple units, learn data from Aspen, and obtain additional information. And actually, as I had asked in class, to do mass balances or to confirm the energy balances in our system and how you can obtain all this information. So with that, I will end there, and in the next video we will be talking about reactors and recycle loops. So thanks a lot. Bye.